Hi, my name is Carmela and I'm working at Reference Lab in Brampton, Ontario. So I'm gonna present you this first case. A 22-year-old female with sickle cell disease presents to the emergency department with shortness of breath. She states that she has chest pain and joint pain. She tells you that she is 8 weeks pregnant and had a similar event at a hospital 4 weeks ago that she had never visited before she was emergently transfused. Her hemoglobin returns at 64. Her last known HBSS was 60% on hydroxyurea, but she stopped taking the medication when she became pregnant. A type and screen is sent with a request for one RBC unit. So the important thing on this case is sickle cell disease, chest pain and joint pain. She's 8 weeks pregnant, emergently transfused, and the HBSS was could be even higher because she stopped taking the medication. So these are the question goals that we want you to learn from the first case that we presented. Number one is saline tube testing can be subjective. Second is send an RBC reagent to all participants with antibody for agglutination strength grading. Next one is to identify an antibody that may not be negative on your antibody screens or identification. And the last one is to link the antibody to the clinical outcome in a pregnancy. So with the reagent red cells and plasma that we provided to you, we ask you to answer about the agglutination strand by saline IAT and by gel method. And this is what we got. So in our lab, we have 2 plus agglutination strand by saline IAT and 66 responders also agreed with 2 plus grading. And few of these responders have a grading of 1 to 2, 1 plus and 3 plus, which are normal for saline IAT method. With regards to gel grading, we can see here a grade of 2 plus and 3 plus, which is expected because this is enhanced method. By gel, this is gonna have some more enhanced reactions. So for laboratories or sites that usually not they don't perform antibody investigation and refer their samples to reference lab, we ask them question like what will they do while waiting for the results, and most of the responders got the right answer, like they'll give a serologically cross-match ABO compatible units until a compatible unit is found. The rest of the responders uh, need to really cross-match the units before they find a compatible one because of the possible underlying alloantibodies on those units. Finding a unit for a known antibody, finding a cross-match unit can be really difficult when an antibody is not identified. Approximately 5% of patients have alloantibodies. The likelihood of finding a cross-match unit is 0.2% for this antibody. And in emergency, give what the patient needs regardless of the antibodies, since most IgG antibodies will cause hemolysis at a later time. So what medical can do is red blood cell exchange to remove the incompatible units in the patient system and replace with RBC negative units, and or give medications to decrease hemolysis. So with the sample that we provided, there is a presence of anti-little k, and some of the participants even remark on dosage of the antibody. And antigen incidence on that says that for homozygous big K, uh, it is found on 0.2% in white population and less than 0.1% in black population. While the heterozygous big K and little k, we can find that almost 9% in white population and almost 4% in black population. While the homozygous little k, like we find most of this in white population, 95% of that, and 96.5% in black population. And we have also to note that anti-big K is more immunogenic than the C antigen. So that means that the lab will see more of anti-big K than the anti-little c. So with the sample that we provided, there's anti-little k on that, and the risk, we asked the risk of the antibody to the fetus. Most of the respondents replied the anti-little k can cause HDFN due to hemolysis of fetal red blood cells, when really anti-little k causes HDFN due to bone marrow suppression of red blood cells. KEL antibodies usually attack bone marrow. Therefore, there will be no red blood cells produced, while other antibodies, they usually cause hemolysis in pregnancy. KEL blood group system, we used to call it KEL for K, big K, and for little k, it's Solano, but now we call big K and little k. 20% of the anti-big K activate complement, but none reported to have hemolysis in saline tube testing. Anti-big K, mostly IgG1 class 1, sorry, but some can be IgM and seen at immediate spin. HDFN are most often affected by suppression of bone marrow erythropoiesis. Critical titer in pregnancy depends on institution. Some have like titer 8 or greater than 8. Some have titer 16 or greater than 16. And in Canada, specifically in reference lab, any positive titer goes to high risk. So we ask a question to the responders or participants, and this is a question that we ask: what is the critical titer in a pregnant patient with this antibody? So most of the participants replied any positive reaction. Some also replied titer of 8, 16, and 32. But in Canadian Blood Services Reference Lab, anything that is positive is considered critical, and we refer them for monitoring to high risk. So based on the history of the case, we knew that the patient received units 4 weeks ago, and most likely the cause of this antibody could be due to a transfusion, and it could be that there was a fetal exposure of red blood cells from previous pregnancy. So the questions that we raised to the respondents is what antigens should be always matched in sickle cell patients. So most of the respondents replied should be RH, ABO-RH KEL match, and some or few replied it should be ABO-RH KEL, KID, DAFI, and SS match. But on the next case, we are going to discuss what is recommended for this. But at a minimum for sickle cell patients, they should receive ABO-RH KEL match units.
Good morning. My name is Minda, and I'm one of the medical laboratory technologists working at NERL, the National Immunohematology Reference Lab in Brampton, and at CBS. And I'm here to discuss with you a case number 2. And this case is about a 27-year-old man with sickle cell disease who presents the day before his red blood cell exchange for a new type and screen. He is A positive and has a negative polyspecific DAT. You perform his antibody identification by saline at all three phases, immediate spin, 37, and IAT. The two things that you have to remember with this case is that this patient is a sickle cell patient and the patient has a negative polyspecific DAT. The goals for this case is to perform antibody identification with multiple antibodies. And we have to keep in mind antibodies that react in immediate spin and IAT to emphasize three phases of tube testing, effect of the enzyme and thiol treatment on antibodies, and assign significance to each antibody identified. So what we did at Neural is that we pooled several like donors plasma with antibodies, and we gave it out to you for identification and testing. And from that plasma, we identified three antibodies, namely anti-Big K, anti-Duffy A, and anti-M. So out of those three antibodies, a lot of people has actually identified the anti-Duffy A, and not a lot for the anti-big K. And for the M, which I personally did the testing, I was not able to really see it in immediate spin, but this is really good because 53 of the participants actually identified the anti-M. And also based on this table or graph, you will see that other participants have identified several antibodies like, big C, big E, and others. So if you have questions about these antibodies, we can have the discussion later on after the presentation. Based on this case number 2, we are about to discuss the different serology tools to resolve identification of multiple antibodies. And we'll be discussing the two major ones. One of them is the papain and physin treatment of the red cells. And the second one is the thiol treatment. That means we're using DTT or AAT. For the papain and physin treatment, the antigens that are destroyed are Duffy, Emin, Shido-Rogers, most of the NOPs, and McCoy. For the antigens that are enhanced or resistant, RHD, RHCE, KID, Lewis, little I, P, big S, little s, and Lutheran, which is only resistant to papain. For the thiol treatment, we have to remember that the biggest two blood group systems that are actually destroyed by thiol are the Kell blood group system and the DOMROC. Based on the serology tools that we just discussed, the next question is, if it were possible to double treat RBCs with physin or papain and DTT, what antibodies would remain? The correct answer is none. So 66 of the participants actually got it right. We have to remember that Duffy A and M antigens are destroyed by physin and papain, and Kell or big K antigen is destroyed by DTT. The goals for this case is how to transfuse sickle cell disease patients in emergency situations. We all know that it's difficult to transfuse urgently when no history is available. Sickle cell disease patients usually have antibodies, and the antibodies may be uncommon or rare. Antibodies are also more likely to be significant and can cause intravascular hemolysis. We must weigh the patient's status with transfusion. The most important things that we have to remember is that immediate spin-only reactivity are usually the safest to drop first, like M, Lewis, P, etc. But we have to remember that's only good for reactivity at immediate spin. If they're reacting at 37 and IAT, that will be considered significant. 733G and 48C mutations are found in the Rh system, and they're usually coded for partial little c and partial little e, and They are usually found in sickle cell disease patients, and they usually don't produce allo anti-little c and anti-little e when we transfuse against them. Then the reactivity that we see does not equal severity. For example, are the KID antibodies. Based on your above testing, in an emergency, which of the antibodies would you first stop matching for, taking into account that the anti-M only reacted at immediate spin? So the correct answer is M, and 73 of the participants actually got it, and the rest of the antibodies or the antigens are clinically significant. The next question is about finding negative antigen units for Duffy A and Cal. And how do we do that? Here's the formula. Number of units required divided by percent of antigen negative for antibody number 1, which is the Duffy A, multiplied by percent of antigen negative for antibody 2, which is anti-big K. So if you wanted to get 1 unit that's negative for Cal and big K and negative for Duffy A, it's going to be 1 divided by 0.35 times 0.91, and that will give us 3 units. That means we have to screen 3 units to get 1 Duffy A negative, Cal negative unit. How many units should you screen to find one compatible unit if you randomly screen units in your inventory for Duffy A and Cal negative units? The correct answer is 3, and 64 of the participants actually got it right, and 38 of the participants doesn't know how to calculate, and hopefully this formula will help you in the future. The current recommendations for SCD matching according to ASH include every patient should receive an extended red cell antigen profile including RH, Cal, KIDS, Duffy, MN, and the S's at a minimum. Genotyping is preferred over serology. All patients should be matched for RH and Cal antigens. Extended red cell antigen matching for KIDS, Duffy, and S's may provide further protection for alloimmunization. In practice, some institutions provide extended match after the first antibody is made or right away depending on inventory. Genotype with the hybrid RHD3A-CE or RHCE-CERN codes for partial C antigen, and no conventional C antigen should be transfused with C-negative red cells to prevent allo-anti-big C development. Based on the current practice, what blood group and antigen-negative units should this patient receive, assuming that the anti-M only reacts at immediate spin? The correct answer is that we have to match for ABO, RHD, RHCE, Cal, KID, Duffy, Big S, and Little S. 54 participants actually got this right. 20 participants included the M, but anti-M only reacts at immediate spin.
My name is Wasim Anani, and I am a medical officer with Canadian Blood Services, and I'll be covering Tier 3 or Case 3 with you. So we have a 40-year-old man from Bangladesh arriving at your hospital with severe stomach pain. He's noted to have a GI bleed with a slowly declining hemoglobin that's now at 75. While in the emergency department, he tells the nurse that his family has trouble finding blood, and a type-in screen is ordered with 1 unit on hold. So some of the important facts from this case. The patient is from Bangladesh, and he notes that his family has trouble finding blood. For this case, we provided plasma, and we asked you to run an ABO reverse type and only your screening cells at immediate spin, 37, and IAT in order to conserve the sample because it was hard for us to get. And the patient's forward typing shows no agglutination with anti-A, anti-B, and anti-A, B. You also run a polyspecific DAT, and it's negative. So based on these results, we asked you what your initial thoughts were. We gave you the option of a cold auto antibody, which 2 people answered, warm auto, none, mixed warm and cold, we have 5, and then naturally occurring antibody. And as many of you are starting to think now, just having these multiple choice answers kind of gives you a hint of what you're looking for, and 36 people were able to start thinking about what it may have been. So now we tell you pre-warming and saline replacement do not resolve the discrepancy. So we ask you, what type of blood should you transfuse this patient? So at this point, most people have already figured out this is a Bombay patient who has an anti-H, which means that they lack the A antigen, the B antigen, and the group O antigen, which is the H antigen, which means that they're going to be incompatible with all blood groups, or I should say all common blood groups. So in order to find a unit for them, you have to order rare blood. So before we jump into Bombay in general, let's first talk about the background of how carbohydrate-based antigens are made, because they're very different from the protein-based antigens. Antigens like KID, KEL, and Duffy are formed very differently from things like ABO, Lewis, P, and the little I and big I antigens. So for proteins, you go from DNA to RNA to the final product, which is the protein. Some of the protein-based antigens also have sugars built off of them, or carbohydrates, things like the M and N blood group system and the S. But there are some that are purely sugar-based. And so for these, what's interesting is that you go from DNA to RNA, and the protein that's built isn't the actual antigen, but it's an enzyme. And this enzyme then goes and tacks on the sugars onto different things, mostly proteins, but it can also be lipids. And then you build out your sugars. And so, for example, when you're talking about ABO, the ABOs are built off of other things. And so if your enzyme is defective, your ABO is defective as a result. This makes it really hard for us to predict what the changes will cause, because the reality is if there's a variant in the ABO gene, which is fairly large, it's hard for us to predict how the enzyme will change, because then the enzyme change will also affect the ABO addition onto a protein or lipid. And that's what makes it tricky. So I know this figure is a lot to take in, so we're going to take it step by step. So when we're talking about ABO synthesis, there are basic building blocks that happen before any A, B, or H, the O blood group, are even built. So in this particular case, for type 2 sugars, okay, which are built on red cells, versus type 1 sugars, which are built on secretions, so things in our plasma, in our saliva, we have precursors. So it's a GalNAc followed by a GalNAc, GlucNAc, Gal. Okay, so the galactose is really the final piece that's built on, and from that we add a fucose. This fucose, which is done by the FUT1 gene here, adds this sugar. This is what makes a group O, okay? Then, in order for us to make our A or B, we have other genes. So for example, the A gene can then go and add another sugar, which is a GalNAc here. Or for the B, we can add just a galactose here. Or they can act together and we get some A and some B. Now, this is important, and it may ring bells now for you, because we know that if you have an A1 versus an A2, right, you have more or less of the A antigen. And if you try to type someone with Ulex europus, which is the H antigen lectin, you'll actually have more binding with the A2 versus the A1. And the reason is that this A here will kind of block this fucose, which gives you the H. So the more A you have or the more B you have, the less H you can bind usually. Okay. Now, when we talk about secretions, they're a little different. Again, they're controlled by a different gene. So if you're a secretor, you've got the FUT2. Okay, and you still have the sugar here, this fucose, but the main difference between these two is that this is a beta 1,3 linkage, and this is just the way that the sugars are linked, versus on the red cell, it's a beta 1,4 linkage. And that's it. That's the main difference between them. And then the sugars will do the same thing where you add the A or the B. And then, of course, we all know that Lewis, which also relies on the secretor, will convert a Lewis A to a Lewis B. Okay, so now that we've done that, let's talk about what happens with a Bombay patient. So a Bombay patient has this entire area completely knocked out, okay? So you've got the precursor, but you never get the addition of this fucose. Same thing happens when you're a secretor. You have the galactose at the end, but you never add the fucose. And for the Lewis, you never add this fucose here. And remember, with ABO antigens, you form naturally occurring antibodies against them. That means someone that sits right on this level will have antibodies against H, naturally occurring, okay? And they won't be able to form Lewis B at all. That also means that in their plasma, they won't be able to secrete the H antigen, or even if they had the A and B antigens present, there is no enzyme that can be there because the enzyme that builds the A and the B antigens actually requires this fucose to be here. So you can't build anything off of it without this H being there. That means your secretions also will lack the A and B antigens as well. Now, with regard to Bomb-based serology, the forward type will appear group O because they don't have any H, A, or B antigen expressed, and in the reverse type, they'll also look group O because it'll look like they'll have an anti-A and an anti-B, but if you put them up against your screening cells, which are group O, it'll also react to them really strongly. Now, when you're testing against your group O reagent cells, because they're all group O and they have that H antigen, which is the precursor to the A and B, they'll all be reactive. If you're running it in gel or solid phase, you won't see the phase of the reactivity, but you'll just see pan-reactivity, and your auto and your DAT will be negative. Now, I said before, the Bombay patients lack FUT2, which is the secretor gene, which means that they can make Lewis A, but they cannot make Lewis B by definition in their saliva. Okay? And para-Bombay patients, which we talk about sometimes, they have the lack of the H antigen on the red cells, but they have the FUT2 or the secretor gene, which means they can express Lewis B. What's interesting is that because they have the secretor gene, agglutination with anti-H is not observed because they can produce the H antigen in their plasma, right? So if you add anti-H to their plasma and try to then add it to a red cell, it's neutralized by the H antigen that's floating around. Other important tidbits that you should know is that they occur in about 1 in 7,600 people of Indian descent. They react really strongly at immediate spin, usually greater than 2+. We usually see them a nice, strong 4+ reactivity. And because the ABO sugars are built off of other sugars, for example, the little I and the big I antigens, you actually, if you were to go and phenotype little I and big I or the P antigens, they'll phenotypically be stronger because the ABO antigens that are built on the end of them are missing. So if you kind of think about a tree, which has a lot of branches, and you go and prune it away, for example, the ABO antigens, the rest of the tree is easier to get to, right? So if you were to go phenotype the red cell tree, and you have less ABO sitting on the surface, you can phenotype other things easier. In this particular case, the other sugars, like little I, big I, and P antigens. So if let's say you have a 2+ reactivity, if you were going to compare it to a Bombay, it might be 3 or 4+ with your human anti-sera if you were going to use that. And we typically see these patients when they're coming through our prenatal bench in neural, and they very often don't cause HDFM because they're IgM based and not IgG. But we do monitor them, and we advise that that our lab looks for IgG in case that it can cross the placenta. So I kind of hinted at this before. We can use things called lectins, and lectins are biologically based proteins. So for example, lectins can be made from animals, insects, plants, and they're essentially ground up, and they're natural proteins that react with sugars. They're used in various biological processes, and so we use that to our advantage because they can recognize some blood groups. Specifically, some of the ones that have been used to identify blood groups are listed here as options, and almost everyone got the fact that ULEX is the main one that we use for H binding. So if you have agglutination with ULEX, that means you have the H antigen present, and they are, by definition, not a Bombay patient. This is a table of many lectins that have been used historically to identify ABO antigens, and in yellow, I just highlighted the ones that identify the H antigen, and you can see ULEX is the last one on here, but there are others on here that actually can bind H antigen. It's just that some of them kind of rose to fame in the lab, and those are the ones that we use most often. Also, some lectins are easier to get than others. For example, getting ones from insects are usually a little bit harder than getting them from plants. And so some of them are just easier to get, and so they were used more often in the lab as a result. But you can see there are actually a lot of lectins that can bind different carbohydrate-based antigens. And there are actually many more than these that have been studied. These are just the most common ones that have been looked at in the lab. And now, for the final question, we asked everyone what is the actual offending antibody that you've identified, and everyone answered anti-H or Bombay patient, which was great to see. So congratulations. So we thought we'd share some interesting tidbits from each of the questions. So for the tier 1, we had a total of 164 techs participating in this, with an average time being spent of 93 minutes. And you can see there's a good spread, and some of these are because of the fact that some of the labs can only do antibody ID versus a full antibody ID. And remember, the anti-little k can be hard to identify if your screening cells don't have a negative cell on there or only have a heterozygous, and you don't get good dosage effect. So 28 were only able to do the antibody screen, and 136 were actually able to perform the full antibody identification. So as a reminder, Tier 2 was our anti-M, Duffy A, and Big K. And you can see that most of the 90 participants that were involved with this case were kind of between the 90 to 120 minute mark, with the average time being spent about 2 hours, which is great to see that it only took 2 hours to identify these 3 antibodies. And as a note, when we send out the continuing education certificates, we'll be using the average times as a part of this. So if you did, for example, tier 2 and tier 1, we'll add the tier 1 and tier 2 times plus this 1 hour time slot to your full time. So you're actually getting quite a bit of time banked up. So for our tier 3 participants, we had 40 participants that were involved. And again, this is the Bombay patient that we had, with an average time being spent of about 80 minutes, which is really great that you were able to identify it so quickly. And you can see it was pretty even keel across the board. Some people were able to identify it pretty quickly in 30, but most people are around the 60 to 90 minute mark. So I know you've banked up a lot of questions over the course of these 3 cases, and we're more than happy to answer them. And we're looking forward to talking to everyone.